BC Calculus, Lesson 11.2, Vectors in the Plane. Excuse me. Had it queued up and it ran off. So here we go. Vectors take a little getting used to. If you've taken physics, you're way ahead of the game. But for me, the only thing that you really need to remember is that when you're adding or subtracting them, break them into x's, y's. And once you do that, the rest really is kind of easy. I mean, you have an x and another x, you put them together, that's your x vector, you got a y, another y. So let's break with it, and here's a vector. What's with those weird parentheses? That means vector. Now, typically the letter is bold, but that would have taken me forever, so I said, heck with that. Find the magnitude and the directions. So if we're going to graph it, so we're going back 1 and we're going up root 3, because this is the point, -1 root 3. And you might have thought, well, wait a minute, you just said it's a vector. Yeah, this is the vector. That's this thing here. And the reason I do this is because now when I say find the direction angle, you say, well, that's not too hard. This is 1, this is root 3, that's a 30, 60, 90, with this side being 2. Across from 30 is 60 degrees. And that was 180 minus 60, so the direction angle is 120 degrees, just like for a unit circle. And the magnitude I've already found is 2, but if you didn't know that, the magnitude is Pythagorean theorem, -1 squared plus root 3 squared equals 1 plus 3 equals square root of 4 equals 2. Magnitude equals 2. So you say, oh, I get it. Vectors just go out to the coordinate points from the origin. No, not necessarily. This vector can be anywhere. We make the assumption from the origin because it's easy, but it could have been here, could have been here, could have been here, could have been here, and we get the same thing. If we started at the point 4, 3, we'd go left -1 and up root 3. They're all parallel, but they're all the same vector. It does matter in the real world how and where we apply a vector, but in mathematics we can put it anywhere. Now the magnitude of a vector I just wrote as magnitude, but we actually write it like this. So I mean it's an absolute value, it's always positive, but it's not an absolute value in that it's a magnitude. You have to do the whole a squared b squared c squared thing. Find the, now we'll go opposite way, component form of a vector with magnitude 3 and direction angle 40 degrees. 40 degrees. So we want to put it in component form. Well, that's actually quite easy. We'll call this vector u. The x is just going to be 3 cosine of 40 degrees, and this is 3 sine of 40 degrees. To which everybody says, well, don't you want to blast it out? And I said, well, you can. There's nothing wrong with that. But I don't, because I'll probably have to do something with that vector in the next part of a problem, and so on, and I haven't lost any accuracy. And then when it finally says your final answer, yeah, I'd put that in my calculator and see what I get. But until then, no, I wouldn't bother. I'd just leave it as is. Now, vector operations are very, very simple. I didn't even write them up. You just add them and subtract them. You can multiply by 0, you can do this and that. The one thing that caused a little problem is what's a scalar? Well, a scalar is a constant. For example, the vector I just had, let's say it was -2u. I would say that is equal to -6 cosine of 30, -6 sine of 30. We just multiply it through to both pieces. And it's saying I want a twice as large vector that points in the opposite direction. That's all it's saying. These are the vector operations. And again, you just add them and subtract them. I mean, I'm not really going to do any work here. I believe 2u plus 3v will get me 1027. I believe u minus v will get me -5, -4. Notice I am drawing vectors. I believe half of the magnitude, I do the whole a squared, b squared, c squared, and then take half of that would be u, huh? Yeah, half of root 10. People say, well, should I do the half before or after? It doesn't matter. You can do it either way. In this case, you should do it before. But it's going to wash out the same way. So play with it. So this is what we're going to do. We're going to be putting it into problems. Airplane flies due east 500 miles an hour. Basically magnitude 500 at a 0-degree vector. There's a tailwind 60 degrees north of east. Well, if you don't know your compass points, you're going to have to figure them out sooner rather than later. Never eat sour watermelon or God knows what. Tailwind is 6 degrees north of east. So this is 60 degrees and it's at 70 miles an hour. So plane just keeps going. What's it actually doing? The real one's going to be something like this. So like I said, break it all down to x's and y's. The wind breaks into 70 cosine of 60 and 70 sine of 60. And I put all this in the first quadrant to make your life easy, but you might have to slap negatives in there, even though it never says negative. If it was down here, then both of these would be negative. If it was going this way, then the y would be negative. So you gotta use a little bit of common sense here. The other one is 500, 0. So you add them together, and you get the new vector. I wrote too big. We really are just adding them. And we should get a vector of, oh, that's right, this is a 30, 60, 90, so I can keep my life simple. Cosine of 60 is half, so 535, and this would be 35, 3. And somebody says, well, okay, what's the magnitude? So we do the whole square root. 535 squared plus 35 root 3 squared equals about 538. I'll go with 0.4 miles per hour. We do have units in here. I should have miles per hour for both of these. And then how do we find the angle? And again, we have to use some common sense. Theta is the arctangent of x over y. So in this case, 35 root 3, pardon me, y over x, divided by 535, which is about 6.5 degrees. So the plane's going to be headed slightly more north than it was planning on doing, and at a slightly greater speed. Going to be doing this over and over and over and over and over. The classic ACT question, some random particle moves in the plane. Its position vector, r of t, is, it really should be shown as a position. Alright, so it doesn't have to be shown as a vector, but it bothers me a little bit that it isn't. So we can just write it as vector. And I would write it as a vector. I'm getting some weird ticky-tacky stuff from my textbook. Differentiate to get to the velocity. Cosine and t. And differentiate again to get to acceleration. Then it says, describe the position and motion of the particle at time t equals 6. Well, at time t equals 6, it's at sine of 6, and it's not really a vector anymore, so we'll say it's at the point sine of 6, assuming it started at 0, 0, sine of 6 and 18, and it has a velocity of cosine of 6, 6, and it has an acceleration of negative sine of 6, comma 1. And if we were asking for the actual velocity, we would, do the actual speed, we'd do a magnitude thing, which I'm going to write in here. So we just basically found the original position. Derivative is the vector velocity, and then the speed is the only one that we need a definition of. We take the magnitude of velocity, and this is a scalar, one number. More problems. Baseball leaves a batter's bat at an angle of 60 degrees. 110 feet per second. And I've noticed these problems always have units that you have to really watch out for. And fielder standing in the direct line of the hit with his glove at vertical reach of 8 feet. Really long arm there. 8 feet. Catches the ball for the out. His feet do not leave the ground. Find the position vector and the velocity vector of the ball at time t's. Now, the velocity, it's already given us a velocity. But we got to watch out. We got gravity popping into this. So now we have to say the acceleration vector is 0, comma, negative 32. No t. Being pulled down. So the velocity vector, well, we were given and make sure I get this right. Yes. X, 110 cosine of 60, which is just 55. And this is going to be 110 sine of 60 minus 32t. So it's being hit up with this velocity, and that's, of course, 55 root 3, but it's being pulled down by gravity. And that's that whole take the integral and put in the c value and see what happens. So what the heck are they asking? Well, that's our velocity, right? That's the position vector and the velocity vector. Well, we don't have the position vector. R of t equals 55t, comma 55 with 3t minus 32. Make that 16 t squared. So now the question is, what time does the fielder catch the ball? So he catches it, he's 8 feet in the air, so that's vertical, we don't know the x, so we have to say 55 root 3t minus 16 t squared equals 8. and that'll be in two cases, one right here when it leaves the bat, another one later. Well, Pythagorean, quadratic formula should get you t equals 5.869 seconds. And I want to make sure I didn't make a mistake, so I'll just blast that into my calculator. I'm a big fan of checking things. And I get just a little bit less than 8, so yeah. And then you can say, how far away was it? Well, how far away is the x value, which is going to be 55 times, excuse me, I need some color in here, I'm going blind with this blue. And that's 322.780 feet. Notice the units pop back up when I actually answer. How fast was the ball traveling when it catches the ball? So we would go with the absolute value of 55 squared plus 55 root 3 minus 32 times 5.869 squared. We should get 107.605 feet per second. Notice how busy and detailed these problems are. They're challenging. They're not easy. They take some time to get good at, so you're going to have to play with them. And again, if you have taken physics, then it's going to help you out a great deal. Another one, and if you want to pause and rewind, I highly recommend that, but in the interest of time, I'm going to keep moving. Particle moves in the plane, find the velocity and acceleration vectors, and determine the path of the particle. Well, the velocity is just the derivative, so we get 3 cosine of 3t and negative 5 cosine of 5t. And the acceleration equals negative 9 sine of 3t, comma, negative 25 sine, cosine, my bad. Oh, I forgot to change this one. Goodness gracious, I do that a lot. Negative 25 cosine of 5t. So then it says determine the path of the particle. Well, this is where you put it into your calculator, and you're going to find some very interesting things. Again, I think this is why mathematicians like parametric equations. They can really go crazy. It'll look something like, and I'm not sure the starting point. Something insane like that.
Interruption. Students, you are about to be released to the Saudi arena for liturgy. You are to leave your books in your period B class. Do not stop at your locker on the way to the Saudi. Senior students, you are permitted to sit on the chairs on the floor of the Saudi. Students with first lunch.
So, another one, and I'm running low on time because this is taking a lot longer than I thought. So I'll just cut to the chase with this. V of t is 4 cosine of t, negative 2 sine of t. A of t equals negative 4 sine of t, negative 2 cosine of t. And then find the velocity at t equals pi over 4, so v of pi over 4 equals, and notice I get rid of the vector, 2 root 2 common negative root 2. A of pi over 4 equals negative 2 root 2 comma negative root 2. Weird. And then the speed, if you use the velocity up above, you should get 10. And if you graph it, you should see that it goes clockwise around the origin. I believe it starts here and goes, boy, that was terrible. Something like that. That's our starting point. Notice how much material is in here. This is the last of it. How do we find displacement? Displacement is where's it going to end up. That's just the integral. We've done this before. A little tricky finding the limits. Keep your eyes and ears open. You'll get it done. Distance traveled is that whole absolute value thing. Well, we don't need it as we showed before. The magnitude's just the Pythagorean theorem. So this will get you distance traveled. So particle moves with velocity vector in a plane at t equals 0 is points here. Find the position at t equals 4. What's the total distance traveled? Again, I'm out of time here, so displacement would just be the integral from 0 to 4 t minus 3 pi. And actually, I should put this up here because this is the x value. Cosine of pi t dt, comma integral from 0 to 4 2t minus pi sine of pi t dt.
Terms in the 100 and 200 balls, and finite equations, use the spelling for the 300 balls. Branches in the 700 and 800 balls,
That equals 8 over 16. And if you wanted the distance traveled, you would put the same thing in except as a square root. So actually I'll do that one and we will call it a day. 0 to 4, monster square root, t minus 3 pi cosine of pi t squared plus 2t minus pi sine of pi t squared. And you will get 33.533, no units. What's the path of the particle look like? It's absolutely bizarre. It actually came really close to looking like what I just drew. It starts here, goes backwards, then it loops. And we could graph this on our graphing calculator if we wanted to see what it looked like. That's a fantastic amount of material. Make sure you put the time in for all your homework. And as always, happy mathing.